Welcome! In this session, we'll tackle the problem matrix block sum. We'll explore its intuition, approaches, and efficient solutions that leverage key concepts in matrix manipulation. Let's dive in. The problem, matrix block sum, asks us to calculate a new matrix called answer based on a given matrix mat and an integer k. For each cell in the matrix answer, denoted as answer, I, j, we calculate the sum of all elements in a submatrix of mat centered at I, j. This submatrix extends k rows and k columns in all directions. If any part of the submatrix exceeds the boundaries of mat, those areas are simply ignored. The input to this problem includes mat, a 2D integer matrix with dimensions mxn, where both dimensions are between 1 and 100, and the values in mat are non-negative integers not exceeding 100. We are also provided a non-negative integer k, which is bounded by the smaller of the two dimensions, m or n. The output is the matrix answer, which has the same dimensions as mat, where each element represents the block sum as described. In the first example, the input matrix mat is a 3x3 grid, and k is set to 1. The output matrix, answer, is calculated as shown. For instance, answer, 0, 0, is the sum of the submatrix that spans from 0, 0 to 1, 1. This includes the values 1 plus 2 plus 4 plus 5, which equals 12. Similarly, answer, 0, 1, corresponds to the submatrix spanning 0, 0 to 1, 2, giving the sum 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is 21. For answer, 1, 1, the submatrix encompasses the entire 3x3 grid, so the sum is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, which equals 45. This pattern continues for all other elements in answer. Each block sum is calculated by summing the values within the corresponding submatrix, based on the given value of k. In the second example, we use the same input matrix as before, but this time k is set to 2. Since the value of k is larger than or equal to the dimensions of the matrix, each block sum includes the entire matrix. The sum of all elements in mat is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9, which equals 45. This means that every element in the output matrix answer is simply 45, resulting in a uniform matrix where all values are the same. This demonstrates how the block sum behaves when the submatrix extends beyond the boundaries of mat and includes all its elements. In the third example, k is set to 0. When k is 0, the submatrix for any cell, I, j, contains only the cell itself, meaning that the block sum is simply the value of mat, I, j. For the given input matrix, where all elements are 1, the output matrix answer will also contain only ones. This highlights a key property of the problem. When k is 0, the output matrix is identical to the input matrix. Additionally, the problem includes constraints that ensure the inputs are valid, such as the size of m and n being between 1 and 100, and all values in mat being non-negative integers. The edge cases include scenarios like a single-cell matrix, large values of k that cover the entire matrix, and matrices filled with zeros. These constraints and edge cases help guide the implementation of a robust solution. To solve the matrix block sum problem, we first consider the brute force approach. The idea here is simple. For every cell in the matrix, we calculate the sum of elements within a submatrix centered at that cell. This submatrix is defined by the range extending k steps in all directions. While this method is intuitive and straightforward to implement, it has a significant drawback. It involves recalculating overlapping submatrices repeatedly. This redundancy makes the brute force approach computationally expensive, with a time complexity of O, m times n times k squared. As the matrix size or the value of k increases, this approach quickly becomes impractical. To address these inefficiencies, we turn to an optimized strategy using the prefix sum technique. The prefix sum allows us to calculate the sum of any rectangular submatrix in constant time after an initial pre-processing step. By building a prefix sum array, where each entry represents the cumulative sum of elements from the top left corner to the current cell, we can streamline the process significantly. With the prefix sum array in place, we can compute the sum of any submatrix using a simple formula. By subtracting and adding appropriate values from the prefix array, we eliminate the need for redundant calculations. For instance, the sum of a submatrix can be derived by combining values from the prefix array at the corners of the rectangle. This makes querying each submatrix sum incredibly efficient. Next, we iterate over every cell in the answer matrix, calculating the sum of the submatrix centered at each cell while ensuring the bounds of the submatrix remain within the matrix dimensions. This optimized approach reduces the overall time complexity to m*n, as both the pre-processing step and the subsequent queries operate efficiently. The key insight here is that by reusing previously computed sums, the prefix sum approach drastically outperforms the brute force method, especially for larger matrices or higher values of k. While other techniques like the sliding window approach exist, they are more suited for one-dimensional arrays and introduce additional complexities when extended to 2 dimensions. Given the trade-offs, the prefix sum approach emerges as the most practical and efficient strategy. The brute force method, while simple, is computationally prohibitive for large inputs. The sliding window technique, on the other hand, is challenging to adapt to 2-dimensional matrices without adding complexity. In contrast, the prefix sum approach strikes a balance between performance and implementation complexity. It requires extra memory for the prefix array but ensures optimal performance by avoiding redundant calculations. This makes it an ideal solution to the matrix block sum problem, offering both efficiency and clarity in execution. By leveraging the prefix sum's ability to compute submatrix sums in constant time, we achieve a robust and scalable solution capable of handling large matrices and high values of k with ease. To solve the matrix block sum problem, we need to compute the sum of all elements within a square submatrix of size 2k plus 1 8x, 2k plus 1, centered at each cell, I, j, of the given matrix. The submatrix's boundaries are constrained by the edges of the matrix itself. While a brute force approach iterating through each submatrix is possible, it becomes computationally expensive as the matrix size and k increase. This inefficient method involves redundant calculations, as overlapping submatrices repeatedly sum the same elements. Therefore, the goal is to optimize this process by avoiding redundant computations and leveraging a more efficient technique. To improve efficiency, we use a prefix sum matrix, which allows us to compute the sum of any submatrix in constant time. The first step is to preprocess the input matrix by creating a prefix sum matrix where each cell, prefix I, j, represents the cumulative sum of the rectangle from the top left corner, 0, 0, to the cell I, j. The formula for this is prefix I, j equals mat I, j plus prefix I1, j plus prefix I, j1, prefix I1, j1, where we first add the current element, then the sums of the rows and columns above and to the left, and finally subtract the overlapping region. For edge cases where indices go out of bounds, such as I1, 0, we treat those values as 0. Once the prefix sum matrix is computed, we can then calculate the sum of any submatrix using this pre-processed data. Using the prefix sum matrix, we can calculate the sum of the submatrix for any cell, I, j, in constant time. To do this, we first define the boundaries of the submatrix. The top left corner is determined by max 0, ik, max 0, jk, to ensure we stay within the matrix limits, and the bottom right corner is defined by min m1, I plus k, min n1, j plus k. The submatrix sum is then calculated using the formula submatrix underscore sum equals prefix br underscore x, br underscore y, prefix tl underscore x1, br underscore y, prefix br underscore x, tl underscore y1, plus prefix tl underscore x1, tl underscore y1. This formula adds the bottom right corner of the submatrix, subtracts out the areas above and to the left, and finally adds back the overlapping top left rectangle. The result is stored in the result matrix for the corresponding cell. The algorithm consists of 2 main data structures, the prefix sum matrix and the result matrix. The prefix sum matrix enables efficient computation of submatrix sums, while the result matrix stores the final submatrix sum for each cell. The time complexity of this approach is m*n for preprocessing the prefix sum matrix, and an additional m*n for calculating all submatrix sums, making the overall complexity m*n. Space complexity is also m*n, due to the storage requirements of the prefix and result matrices. By leveraging the prefix sum, we avoid redundant computations, ensuring that the algorithm is both time and space efficient, even for larger matrices. The pseudocode implementation begins by initializing the prefix and result matrices to the size of the input matrix. The first step is to compute the prefix sum matrix by iterating through each cell and applying the prefix formula, while handling edge cases where indices are out of bounds. Once the prefix sum matrix is prepared, the second step computes the sub-matrix sum for each cell. For each cell, I, j, we determine the boundaries of the submatrix using max and min functions to ensure we stay within the matrix limits. We then calculate the submatrix sum using the prefix sum formula, account for overlapping areas, and store the result in the result matrix. Finally, the result matrix is returned as the output, containing the computed block sum for each cell. Here, we begin by defining the matrix block sum function inside the solution class. The first task is to determine the dimensions of the input matrix mat by extracting its number of rows m and columns n. To simplify the computation of block sums later, we create a prefix sum matrix named prefix with an extra row and column filled with zeros. This extra space helps handle boundary conditions more easily. Next, we populate the prefix sum matrix. For each element in the input matrix, we calculate its corresponding prefix sum by adding its value, the prefix sums to its left and above, and subtracting the overlapping region's prefix sum to avoid double counting. This results in an efficient way to compute cumulative sums for any submatrix. Finally, we initialize a result matrix with the same dimensions as the input matrix, where we will store the computed block sums. The last part of this code snippet outlines a nested loop structure to traverse each element in the matrix. Here, we determine the boundaries of the block for each element, ensuring the indices stay within valid matrix limits using the max and min functions. The block boundaries are then adjusted to align with the one-based indexing used in the prefix matrix. Specifically, we increment each boundary index by 1. With the boundaries defined, we calculate the block sum for the current element using the prefix sum matrix. The formula combines the cumulative sums of the rectangle defined by the block boundaries, subtracting the sums of areas outside the block and adding back the overlapping region. This ensures the result reflects only the sum of elements within the desired block. The computed block sum is then stored in the corresponding position of the result matrix. Once all elements have been processed, the function returns the result matrix, which contains the block sums for the entire input matrix. This approach leverages the efficiency of prefix sums to compute block sums in constant time for each element, resulting in an overall time complexity that is well suited for large matrices. Here, we begin by defining the method matrix block sum, which takes in a matrix mat and an integer k. The matrix dimensions are determined by m and n, representing the number of rows and columns, respectively. To simplify boundary calculations later, we create a prefix sum matrix with one extra row and column. This additional space helps us avoid boundary checks while building the prefix sum. Next, we populate the prefix sum matrix. For each cell in the original matrix, the corresponding cell in the prefix sum matrix is calculated as the value of the current cell in mat, plus the sum of the values from the row above and the column to the left, minus the overlapping region already counted at the top left diagonal. This formula ensures that every cell in the prefix matrix represents the cumulative sum of the rectangle from the top left corner down to that cell. Once this step is complete, we initialize a result matrix to store the final answers. The final part of this slide sets up the loop to calculate the block sum for each element in the result matrix. For every cell in the result matrix, we determine the bounds of the block by using the parameter k. We calculate the row and column indices that define the top left and bottom right corners of the block, ensuring they stay within valid matrix boundaries using math.max and math.min. Now, since the prefix matrix uses 1-based indexing while the original matrix uses 0-based indexing, we adjust the block boundaries by incrementing each of them by 1. These adjusted indices are then used to compute the sum of the desired block using the prefix sum matrix. The formula for the block sum employs the inclusion-exclusion principle. We start with the total sum of the region up to R2 and C2, subtract the areas above and to the left of the block, and finally add back the overlapping top left corner that was excluded twice. This gives us the exact sum of the block defined by the boundaries. Once the block sum is calculated, it is stored in the corresponding cell of the result matrix. After processing all cells in the result matrix through these calculations, the method returns the result, which contains the block sums for all positions in the input matrix. This approach ensures efficiency by leveraging the prefix sum matrix to calculate each block sum in constant time, resulting in an overall time complexity of O, m*n, where m and n are the dimensions of the input matrix. To solve the matrix block sum problem, let's start by understanding the input and the first step of the solution. Here we have a small 3 by 3 matrix and a block size of k equal to 1. The goal is to compute the sum of all elements within a k-radius block for each element in the matrix. To make this process efficient, we first build a prefix sum matrix. This matrix has dimensions slightly larger than the input matrix, with an extra row and column filled with zeros. These extra spaces help simplify the boundary calculations later. At this stage, the prefix matrix is initialized with zeros, and will populate it with cumulative sums in the next steps. Now, we calculate the prefix sums by iterating through the input matrix. For each element in the matrix, the prefix sum at a given position is calculated using the formula, the value of the current element plus the sum of the elements above it and to its left, minus the overlap at the top left corner. For example, at position 1, 1, the prefix sum is 1. At position 1, 2, it becomes 3 because we add 2 to the previous sum. This process continues row by row, and by the end, we have a fully computed prefix matrix. With the prefix sums ready, we can efficiently calculate the block sum for any position in the matrix. For instance, at 0, 0, the block boundaries are determined by k, and the block sum is calculated using the prefix matrix. Using the formula, the block sum is 12 for this position. After calculating the block sum for 0, 0, we continue to compute it for the other positions in the matrix. For instance, at 0, 1, we use the prefix matrix and the same formula, adjusting the boundaries based on the current position in k. This results in the final block sums for the entire matrix. When all calculations are complete, the resulting matrix is as shown. Each value in the resultant matrix corresponds to the sum of the elements in the k-radius block for that position. This example demonstrates how the prefix sum matrix allows us to compute these sums efficiently, even for overlapping blocks. Now let's consider a different scenario where k is much larger than the dimensions of the matrix. Here, with a 2 by 2 matrix in k equal to 10, every block will include the entire matrix, since the block boundaries extend beyond the edges of the matrix. First, we compute the prefix sum matrix as before. The prefix sums are derived from the cumulative sums of all elements in the input matrix. Once the prefix matrix is computed, the block sum for every element is simply the sum of all elements in the input matrix, since all blocks encompass the entire matrix. This results in a uniform output matrix where each value is 10, the total sum of the input matrix. This edge case highlights how the method handles scenarios where the block size exceeds the matrix dimensions. Now let's consider a non-square matrix to see how the solution generalizes to different dimensions. The input matrix here has 2 rows and 3 columns, and k is equal to 1. As before, the first step is to compute the prefix sum matrix. Using the same cumulative sum formula, we calculate the prefix sums row by row. Once complete, the prefix matrix reflects the cumulative sums for this input matrix. This step prepares us to compute the block sums efficiently, regardless of the matrix's shape. With the prefix matrix ready, we calculate the block sums for each element in the non-square matrix. For example, at position 0, 0, the block boundaries are determined by k, and the block sum is computed using the prefix matrix. Similarly, we calculate the block sums for all other positions in the matrix. The result is a new matrix where each element represents the sum of the elements within the k-radius block for that position. This example illustrates that the solution works seamlessly for non-square matrices, maintaining the same efficiency and accuracy as with square matrices. In this problem, the time complexity of our solution is determined by 2 main steps. First, we construct the prefix sum matrix. This involves iterating through each cell of the input matrix using a nested loop. Since the input matrix has dimensions m by n, this nested loop executes m multiplied by n times. Within each iteration, only a constant amount of work is done, such as adding or subtracting values, so the time complexity of this step is O, m*n. Next, we calculate the block sum for each cell in the result matrix. Again, we iterate over all m*n cells of the input matrix. For each cell, we determine the boundaries of the block and use the prefix sum matrix to compute the block sum in constant time. This involves a maximum of 4 lookups and a few arithmetic operations. Since these operations are constant for each cell, this step also runs in m*n time. Combining these two steps, the overall time complexity of the solution is m*n. The space complexity of our solution is primarily determined by the additional matrices we use. First, we create a prefix sum matrix, which is slightly larger than the input matrix, having dimensions m+1 by n+1. This is done to simplify boundary handling during calculations. While the constants added by the extra row and column are negligible in big O notation, the space required scales with the size of the input matrix, leading to a complexity of m*n. Additionally, we allocate a result matrix of size m by n to store the block sums. This also contributes m*n to the space complexity. Apart from these matrices, the solution uses only a constant amount of space for variables like loop indices and temporary values, which is 1. Since the prefix sum matrix and result matrix dominate the space usage, the overall space complexity of the solution is m*n. When we compare this optimized approach to a naive method, the difference in efficiency becomes clear. In the naive approach, we would calculate the block sum for each cell individually by summing all elements in the corresponding submatrix. For a cell, summing the submatrix takes k squared time in the worst case, where k is the size of the block. Since this operation is repeated for all m*n cells, the total time complexity becomes m times n times k squared. However, in the optimized approach, we leverage the prefix sum matrix to reduce the computation for each cell to constant time. This reduces the total time complexity to m*n. The optimized solution is especially advantageous when the block size k is large relative to the matrix dimensions m and n, as it eliminates the redundant computations inherent in the naive approach. To understand why the time complexity of our solution is m*n, we can look at the mathematical proof. For the prefix sum construction, each cell in the prefix matrix is computed using a constant number of operations, including accessing the current element and up to 3 neighboring cells. Since this process is repeated for all m*n cells, the total time complexity is m*n. Similarly, when calculating the block sum for each cell in the result matrix, the boundaries are determined, and prefix sums are accessed in constant time. With m*n iterations for the result matrix, this step also runs in m*n time. For space usage, the prefix matrix and result matrix are the primary contributors, both requiring m*n space. Finally, it's worth noting that the time complexity remains m*n, regardless of the input dimensions or values, meaning there's no distinction between best, average, and worst cases. In conclusion, the optimized solution demonstrates its efficiency by significantly reducing the time complexity compared to the naive approach. By pre-computing the prefix sums, it eliminates redundant calculations and allows for constant time block sum computations. While this optimization introduces additional space requirements for the prefix matrix, the trade-off is well worth it for the substantial improvement in performance. This makes the approach especially suitable for large matrices or scenarios where the block size is considerable, ensuring that the solution remains scalable and efficient. When solving the matrix block sum problem, there are a few common mistakes to watch out for. One frequent error is mishandling overlapping submatrices. For example, if the submatrices partially overlap or extend beyond the matrix boundaries, you might accidentally double count some elements or exclude important edge cases. To avoid this, carefully validate boundary conditions and ensure your logic handles out-of-bound indices gracefully. Another pitfall is relying on inefficient brute force solutions. While manually summing each submatrix might work for small matrices, this approach becomes computationally expensive for larger matrices, resulting in a time complexity of n²*k squared. Instead, consider more efficient techniques like prefix sums or sliding window methods, which significantly reduce computation time. Additionally, errors in setting up prefix sums can lead to incorrect results. For instance, failing to initialize the top row or left column properly could throw off the cumulative calculations. Testing thoroughly with edge cases ensures your prefix sum logic works as intended. Lastly, if the problem involves floating point numbers, remember that direct equality checks can cause precision errors. Using epsilon-based comparisons or integer representations can help you avoid these issues and produce accurate results. Misinterpreting problem constraints is another common issue to be mindful of. Pay close attention to details like the matrix size, the valid range of k-values, or whether negative numbers are allowed. Overlooking these constraints may lead to inefficient solutions or runtime errors, particularly if your implementation fails to account for edge scenarios. Now, from an interview perspective, this problem is a great opportunity to showcase your ability to recognize optimization patterns. For example, identifying the potential to use prefix sums or dynamic programming demonstrates a strong grasp of computational efficiency. You should also be prepared to discuss the trade-offs between different approaches. While brute force might be conceptually simple, it's impractical for large inputs. Optimized methods like prefix sums or sliding window techniques are faster but require careful pre-processing and implementation. Additionally, boundary handling is a subtle yet critical aspect. Interviewers often include test cases where submatrices exceed the matrix bounds, so ensure your solution can handle these gracefully. Finally, scalability is a key focus, especially for large matrices. Highlighting how your approach reduces redundant computations and improves time complexity, say, from O(n squared * k squared to O(n squared), can leave a strong impression on your interviewer. To deepen your understanding of the matrix block sum problem, it's helpful to explore related problems that build on similar concepts. For example, LeetCode 304, Range Sum Query 2D Immutable, is an excellent starting point for mastering the prefix sum technique in 2 dimensions. It lays the foundation for efficient submatrix sum calculations. Of course, LeetCode 1314, the matrix block sum problem itself, directly applies these concepts, emphasizing the importance of optimized submatrix summation. For a more advanced challenge, LeetCode 363, Max Sum of Rectangle No Larger Than K, introduces optimization constraints, pushing you to think critically about balancing efficiency with problem requirements. And for a variation involving dynamic programming and pathfinding, LeetCode 174, Dungeon Game, requires you to navigate through a grid while managing state transitions. These problems collectively enhance your problem-solving skills and prepare you for a wide range of grid-based algorithm challenges. There are several alternative approaches you can consider when tackling the matrix block sum problem, each with its own trade-offs. Using a prefix sum matrix is a popular choice, as it allows you to pre-process the matrix in O(n squared) time and then compute submatrix sums in O(1) time. While efficient, this method does require additional space to store the prefix sums. Another option is the sliding window technique, which is particularly useful when k is fixed. By maintaining a running sum as you slide over the matrix, you can achieve an O(n squared) time complexity while using slightly less space compared to prefix sums. For problems with specific setups, a divide-and-conquer approach might be effective. By splitting the matrix into quadrants and solving recursively, you can reduce redundant calculations, though this method is less commonly used. Finally, dynamic programming is an excellent choice for variations that require path-based optimization, such as finding maximum sum paths. While highly flexible, dynamic programming requires careful attention to state transitions to ensure correctness. Each of these methods has its strengths, and the choice of approach depends on the problem's constraints and requirements. In conclusion, we've discussed how to efficiently solve the matrix block sum problem using a prefix sum approach. This method highlights the importance of pre-computing results in matrix problems for enhanced performance. Thank you for joining, and stay tuned for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!